think we're probably ready to get started. No one? Yeah. Okay. In this breakout session, we're going to go over content encryption. I want to basically go over some basic history, as well as when to use certain algorithms, and then how it relates to Alfresco. I am Brian Long. I am a consultant with Alfresco and been here for 16 months to stay on the months topic. The way I want to start out with this whole discussion is kind of some user stories or business stories around why you want encryption, who wants to encrypt things, and what you're trying to protect, essentially. And we'll go into cryptography in general, as well as how it applies to Java, and then into the Alfresco repository with the new feature that's coming with Alfresco 5.0. And that module is the CryptoDoc module. So with user stories, the first question is why? Why would anyone want to encrypt things? Because it makes some things more complicated when you try and do that. And you usually don't want to encrypt everything, because there's a hit involved when you do it. But the main reasons boil down to two things. You want to protect your content for your business, and also the law sometimes requires it. And so maybe you don't want to encrypt it, but the law says you have to. And we'll go over some of those examples. When you're trying to protect your content, a lot of people think of hackers, someone coming in from the outside. They're going to get your content and be able to use it against you in some way. A lot of people forget about, and a lot of businesses forget about, the internal users and protecting your content from rogue users or just unauthorized users that shouldn't have access to it. And that could include developers, administrators. In your production systems, under certain laws, only certain people should view it, and those people are not included. You also have, with recent news with the NSA, and I'm sure there's people thinking the same way in Britain with the MI5, there's concerns of government spying on you, or China. So you're trying to protect from all kinds of people and entities when you're doing this. Government, in the government industry, the financial, banking, education, medical, pharmaceutical, pretty much any regulated entity is going to need encryption. It's in the laws everywhere. There's actually a basic law that covers just about everything that requires encryption in most countries. There's certain countries that require encryption just if you store any document there. It's like you have to encrypt it, even either for a business reason or because the law says you have to. So pretty much everyone wants or needs to encrypt, whether you even want to or not. But one of the use cases or user stories is around medical and pharmaceutical, and the infamous HIPAA, which was an act from the 1990s in the US that essentially it doesn't, I don't think it explicitly says you have to encrypt this. That came along a little later with this high-tech law that came around in just 5 years ago or so. But with HIPAA, it says only the patient and the doctor, and only for a certain period of time should these people be able to access it. And so it put these controls for any medical or pharmaceutical organization or insurance that's holding these documents to make sure only certain people have access to it. And I don't know how stiff the penalties are, but you definitely don't want administrators accessing someone's EKG that was submitted because they're trying to get life insurance or something. It's just, you need to be able to protect from that happening. And in some cases, you could use the security of the system to help you with that, but encryption takes that step further. So if someone can bypass that security, can they still get to the document? All of that information that's determined to be protected is this PHI, protected health information. And with this later act, they explicitly said that data should be unusable, unreadable, and indecipherable to unauthorized users. So that, without saying encryption, I mean, it has the word cipher in it, I guess. It's saying encrypt that. So finance has big use cases around it, and this was what everyone likes to term the deregulation act of the banks, but it had this other rule in there, the safeguards rule, which essentially says you need to encrypt all your personally identifiable information or protect it in some way. And encryption is always the implementation of that. So, and then with different countries, in this case, I'm just going to talk about United Kingdom and the U.S. We have general rules. It doesn't matter what industry you're in. If you allow personally identifiable information to get out, you could be held liable. So that's part of the Data Privacy Act or something. I forgot to put the name of it on there, but and the United Kingdom has a Data Protection Act, and then every state could have their own. It's so convoluted right now that you almost have to default to the most secure method on all your documents just to make sure you're covered, unless you have someone who's a really good expert in law in that area. So knowing that you need to put encryption in place, I'm going to just go over some cryptography notes. And I wanted to start off with a little bit of a history piece to it. And this is just a clay tablet that I just took off the internet. But the first use of encryption in history that's been confirmed was 1500 BC. So we've been doing this for a long, long time, trying to hide stuff from people. And it was on a clay tablet in the Middle East, the present-day Middle East. There's also more substitution ciphers, which I'll kind of briefly get into, but that the Hebrews were doing in 500 BC, and it's essentially something like this, except in a different, not in the Arabic alphabet, but you're substituting letters in what you're trying to encrypt. So every A becomes an N, every N becomes an A, and so on and so on. It works really well unless you know that process, and then it's really easy to pull it apart. An interesting next thing I want to talk about was in 800 AD, we start seeing people actually writing information about how to break these kinds of codes. So for a long time, people were doing this stuff, and there was no common knowledge, like how do you try and decipher this? And a guy, Al-Kindi, I might be butchering his name, but he wrote a whole manuscript on how to decipher these simple substitution algorithms, trying to find common letters and going about the business that way. And then very few people know, and I didn't know this until I researched it, but Edgar Allan Poe was very big on breaking algorithms. It was just one of his little things. I guess write some poems and then break some algorithms. People would submit cryptic messages, and it was a challenge to him, and he would just try and go about doing it. Then it started to get big with World War I. The Zimmerman telegram, I don't know how many people know about that, but that's been kind of the people say what caused the U.S. to enter World War I. The Germans had a cryptographic message to Mexico to form an alliance to join the war on their side. It was intercepted. The British broke it and then informed us. And we're like, oh, we need to do something about this. And from that point, encryption really started getting big. And that's where I have the Enigma machine, which is the most famous crypto device, electronic crypto device. It's nice and portable, but that was developed in Germany right after World War I, and in wide use for businesses and governments coming into World War II. But they kept changing it, making it more and more complicated, adding rotors, and to try and make it as unbreakable as possible. As everyone knows, it was broken, and then they kept modifying it. It got broke again. So at that point, cryptoanalysis, which is the field of trying to break these things, just boomed. And that's, in my opinion, that's kind of the start of real computer science. I mean, really digging into the mathematical theories and everything behind it. And that's where you get Alan Turing being considered the father of computer science for his work involved in breaking that. When you get into modern cryptography, although these things aren't technically cryptography, I like to try and classify them in there because it's kind of a series that you can go through to see what use cases you want to apply each of these for. So we're going to go through hashing, encoding, and encrypting, and I have more details on the next slides. So hashing, I like to just say it's a one-way encryption, and it's incredibly lossy. It essentially, you could say it compresses it down, but you're hashing something down to a set static length of bits that here is represented as hexadecimal, but you have a lot of different hashing algorithms available, and they essentially do similar things. The point of this is that this clear text on the left, in this case Alfresco 4.2, would always hash to this value. And so every time you plug that in, it always, same thing, same thing. Makes it very good for password authentication because you don't have to store the person's password, you store the hash. So you're storing an encrypted version of their password, and then you're just comparing the encrypted versions. That's a great way of protecting yourself from your own administrators and developers. They can't find that person's password unless they're sniffing on the login part of it, but nothing is persisted in your database with that user's password. So kind of gets you a step into trying to protect yourself from yourself in a way. And you can see that with Alfresco 5.0, very subtle change, but I don't think a single one of these characters is the same as the one above it. I mean, it's gobbledygook, we like to call it. There are an infinite amount of things on the left side that would hash this exact same value, but the likelihood of that is so low that it's usually not even considered. So when you log into a website, you could use a different password and possibly get the same hash. The next thing I want to talk about is just encoding and decoding. It's a completely different use case. In computers, you have your bits and your bytes, and how do you represent that stuff to a user is an encoding of it. So ASCII, I think 45 is a capital A. I don't know. I'm just throwing that out there, but you try and represent bytes with certain characters, and like a URL encoding, you're changing how that representation happens by trying to remove certain characters and have a smaller character map. And the use case, When you look at base 64 encoding, which is at the bottom here, it looks encrypted. You could call it a keyless encryption, but it's not really encrypted or scrambled. And I mean, it just looks scrambled. But when you look at the algorithm behind this, it makes sense why it looks so daunting. But here, you're just trying to represent all 256 different characters that you could find in your standard UTF-8 and ASCII. Trying to represent it as 64 different characters. This allows you to embed things inside XML, inside HTML, multi-part MIMEs. Likewise, you're trying to embed text inside of a URL that doesn't conflict with your typical URL slashes and colons and ampersands and question marks. So this is great for putting your data into an envelope of some kind. That kind of leads into the old encryption. The first types of encryption are the popular ones, the substitutions and changing character orders. All of this, I don't know if you could tell what it is, but it should be pretty easy because I've been reusing it. But Alfresco Enterprise. Just write it backwards. Makes it hard to, at least a search thing won't find that. Add letters onto the front and back, or mix that all together. A lot of things you would do in school when you're passing notes to your prospective girlfriend or whoever, trying to keep the teacher from being able to read it. These are generally just a monoalphabetic cipher. Polyalphabetic is Enigma, where every character that changes as you type, it changes what the substitution really is. And that makes it really, really hard to figure out. So I don't know specifically how it works. That's quite a case study. So this leads to today's two big encryption methodologies. One is symmetric encryption. This one's relatively easy to visualize in today's world. You go home with a key in your hand. You unlock your door and you get into the house. When you leave, you lock it back up and you're gone. One key to go either way. Makes sense, simple idea. Most of these are block ciphers. There are stream ciphers, which I don't want to get into on this, but block cipher algorithms, these are your popular ones. DES is the old one. Triple DES or 3DES, I think was IBM, came up with the idea. And it's basically apply DES forward, apply it backwards, and then apply it forwards again. If you duplicate a 56-bit key 3 times, you essentially encrypt it, re-decrypt it, and then re-encrypt it. They did it that way so it was backwards compatible, because there's a whole lot of documents that were encrypted this way. Let's make a stronger one that we don't have to re-encrypt everything with. And this is pretty strong. This was submitted along with, I'm going to butcher the name of that one, but I'll get to it on the next slide. But the AES, what became the AES algorithm, which was a competition sponsored by the government, probably DARPA or NIST. I can't remember that one. And they won. And that means that most of the government requires AES, the US government, that is. And I think it's been adopted pretty much everywhere. And then there's conspiracy theories. Because they selected that one, that means they broke it and they know how to get into it. So. This is the name of it. I think it's the guy's name. Rijndael Cipher, their cipher here. It's when it won, it was classified as the advanced encryption standard, and so it's known as AES. It's a block cipher. This kind of try to visual. This is from Wikipedia. To try and visualize what a block cipher looks like. with an 128-bit encryption, which is 16 bytes if you divide it by 8. You have a 4x4 block you can try and visualize it as. So it encrypts 16 bytes at one time, and then goes to the next 16, encrypts, encrypts, encrypts. And they all work that way. All these symmetric ones, the popular ones. You run into pattern problems when you do this, and I'll show it on the next slide. But to get around those, there's cipher modes on how to encrypt these. And I mean, you can dive into this. Some of these you can thread how you're decrypting, thread how you're encrypting. Maybe only one of them can be threaded, the other one not. There's advantages and disadvantages to different kinds of modes and how you apply it. But on both sides, whoever's encrypting, whoever's decrypting, needs to do the same thing. That's kind of part of the key. You have a key, 128-bit key. You have a mode that you need to know. And you have possibly an initialization vector that you need to know. There's a lot of keys to decrypt these. Initialization vector is something, it's a seed that you can put in, like another key. So it affects the rest of the encryption. The reason why you do that is, if we start off with this image, here's your plain text Linux Penguin image. And when you think of the image itself, you have a whole lot of white space on this image. It's crazy how much white space is on there. All that white space, every 16 blocks, is going to look exactly the same. And so they're going to encrypt exactly the same way. And so you can see it's just a repeating pattern. And so if you actually look at it with certain keys, you could still see the image in that pattern. It's a great way of representing the pattern analysis of an encryption algorithm. You can't really do the same thing with a document, a text document. But because you can do it here, that means there's a pattern to those, and that means someone can figure something out to break it. So, bad idea. And especially if you have an image of a document, there's a whole lot of white space on that too. So you kind of see what kind of document it looks like, which can help you try and determine how to decrypt it too. So with an initialization vector and using those cipher modes, it looks like your old CRT TV when you hit a channel that doesn't receive. At the top of this, I have a PDF header. Most PDF headers look, the first two lines are that, represented as ASCII. Whatever the heck these mean, I don't know, but they all have that. And it depends on your PDF version, but if you're storing millions of PDFs, you could have millions of PDFs with the exact same first two lines. Those first two lines are actually happen to be exactly 16 bytes. So if you were to encrypt it without initialization vector, every document, if you encrypt them all with the same key, would look exactly the same on the first 16 bytes. A crypto analyst would look at that and say, wow, all these documents start the same way. They already have insight into your data because of that. And that could help them along the line trying to decrypt it. The other methodology of encryption is asymmetric. This one is a completely different use case. It came about in 1970. Really ingenious idea. If you try and go back living in 1960, I don't know how you visualize this, even today, in a common use scenario. I try and think of like a post office box where you can put letters into it, but it's locked up. You can't get to it. Only the postal man can unlock it and get all the mail out. So anyone can put stuff in, but only authorized individuals can get to it. And that's kind of the idea here. You share a public key so that anyone can encrypt data. And they send it to you, and you, with the private key, you're the only one that can decrypt it. That methodology not only is the basis behind internet communications, it's also the basis of trusting individuals, signing things, because they all involve two parties. Anytime you have two parties, that's your algorithm. Well, your methodology, and most likely the RSA algorithm. NIST actually standardized on DSA. I haven't seen it in use myself, but I'm guessing the government uses that one all the time, as opposed to the companies. So, the differences, and this is something I always like to explain, but you see a lot of use of asymmetric algorithms for things that should be symmetric. If there aren't two parties involved, why choose asymmetric when symmetric is faster and it's more secure? An AES 256-bit encryption, which is theorized to be so secure that it would take all the energy in the world to break it or to exhaust all the keys. I mean, it's a whole lot of different possibilities. They're saying that RSA 15,000-bit is as secure as that. And generally, the higher the bit, the slower the algorithm is going to perform. So with the discussion we get into with Alfresco, symmetric, when Alfresco is doing the encryption and doing the decryption, symmetric is the way to go. Now, if the client is going to do the encryption, which is a possibility that you may want to look into, but then you would go to asymmetric. They would encrypt it before even sending it to Alfresco. And then Alfresco would be able to read it, index it if they want, those kind of things. Then we kind of do a quick look at Java and how it addresses encryption. Java has a Java cryptography extension. Whenever you hear someone say JCE, you say it real fast. It almost sounds like a word, but it's an acronym as usual. This extension's been in place for a long time. It handles three major functions: the generation of keys, storage of those keys, and then the use of those keys to encrypt or decrypt something, which is a cipher. So when you're doing those three different things, there's different things to be worried about. With key generation, you need randomness. Otherwise, it becomes predictable. That one's probably the least thing to worry about because it's still pretty random even. Usually it's pretty random. Key storage is a huge thing to be concerned about with security, because if it's just sitting on the box, the key, then any administrator can get to it. And they can go rogue, grab all your documents, and run. You need to secure it from yourself, which is really, it's kind of, you're trying to limit how many people can do it and who you trust. But you also have, with the cipher, performance concerns, because encrypting and decrypting is overhead. It takes CPU, not so much memory, but mostly just CPU, unless you really thread it. In Java, the JCE extension, there's a default JCE provider on every Java installation. The one that comes with Alfresco will have, it's an Oracle Java installation, so it has Oracle Java JCE provider. Implements your AES, triple DES, and RSA, so you can do all those basic things. It's limited on how high bit level you can go. You have to download another file for export reasons, because I guess we don't want to give other countries the ability to encrypt things better or more strong encryption. IBM's JVM comes with its own provider, basically provides the same things. And then there's the better solution. This is all software, as well as Bouncy Castle. You have there's hardware options available. I have one on here that I've worked with in the past. And it's literally a hardware device that you plug into a server. It could be a card. It could be multitude of different, it come in different shapes and sizes. But the idea is it has an API layer. You have to log into the device. You stream your content into it. It encrypts it and pumps it back out. That way no one can touch the key unless you can break this whole box, which is a whole other story. A lot of these companies have been doing it for years, and this is the recommended and trusted solution. Also, yeah, on this box, because of the whole logging into it, and even if you log into it, you can't see the key. I mean, you can see the alias of it, but you don't have access to that data. So an administrator administering this still is going to have a difficult time compromising it. So the other thing I wanted to mention here, when you offload it to things like this or a PCI card or something, it also offloads that CPU usage. So instead of Alfresco itself taking the hit, let's have this do it. So you can just offload it. I can't imagine that much of a performance hit on your encryption and decryption unless you have really, really high loads, but you'd benefit from that as well. And some of these also have key generation as well. So you have a better random number generator, better keys, all that. And then we get into Alfresco. And I want to just give a basic overview of the repository first. It's really, I don't call it an ugly diagram, but there's two main entry points into Alfresco on your typical system. Whether it's applications or an actual user hitting the repository or the user coming through share to hit the repository, it all comes through that repository, which interfaces with Solr. And then there's three different places where we store things. We have index storage, metadata and other configurations within Alfresco storage, and then the content itself. When you're setting up a secure system with Alfresco, these are the three things you want to worry about. This is your data at rest. There are database encryption solutions with database vendors specifically. Should be transparent to Alfresco. I've seen it work, so it should be good there. There's also hardware encryption that you can do. And those, it could be on the actual disk controller or the file system, but it's meant to be transparent. And so all content that goes into it is encrypted. And Alfresco doesn't care or know, we're good with that. The thing is, once it's mounted on there, anyone that has access into that drive can see it. There's no controlling, well, or it'd be hard to do, especially with Alfresco on the top, controlling who can log into that system, go into that directory, and then just grab whatever files they want. The unencrypted, so yeah, it's unencrypted to everyone. Within Alfresco, you can implement encryption with the content store, which we're going to see here in a second. Or you could do it at the content service level, which takes it a step higher. And this is transparent, the content store. With the content service, you could discriminate on the data based on an aspect or a property and encrypt it, like encrypt only personally identifiable information if you wanted to do that. So in Alfresco 5, we have the CryptoDoc module. The goal behind it is to encrypt all, or encrypt contents at rest. That's your main thing. We wanted to be able to support third-party cryptographic systems. Even if it's not JCE compliant, you could possibly write your own modules to hook into it. And architecture independence is great for being able to deploy it anywhere. We don't want to rely on the type of file system or the type of database, and just allow it to happen just by installing a module. And we want to be able to support key rotation in case one is compromised for whatever reason. The basic design, you have the Alfresco APIs. However that request gets in there, it's going to do stuff with metadata storage, hit content service, content store, and store it. And so the implementation here is to redirect from content service to hit a crypto content store and then store it. And so that uses the whole framework that does all the work for you through some configurations. It will also store information in here in the metadata within Alfresco. And so just to be aware of that. The other methodology, which is not implemented in 5.0, is to intercept it at the content service level. I've written this piece. If you're interested in knowing more about it, I can share that information. Both of these methodologies are going to encrypt and decrypt streaming content. You can have 200 gigabyte files, and it's not going to like load it all into memory, or you have to worry about any of that stuff. This implementation in 5.0 is transparent, and it uses key encrypted keys. If you're not familiar with it, the idea is you have a master key or a set of master keys, and you have content as well. So you have content down here. Encrypt that content with a key, and then encrypt the key with the master key and store your encrypted key in the database. So what we do is we encrypt every single document with a different key. Really makes it hard for pattern recognition, because now everything's just completely different. So our initialization vector is 0, because we don't care about the patterns. Every document's different. And all those keys are stored up here with the algorithm used to encrypt it. So if you change the algorithm, it'll support that in the future. Your master key is then stored in a key store, hopefully a hardware device, to prevent someone from compromising it. But if you want to rotate it, there is a call that you can make to switch a key from one to another, a master key, and it will go in and re-encrypt all the keys in the database that were used, that were encrypted with that old key. This way, the key rotation puts a load in the database, doesn't even touch content storage. It makes it a whole lot quicker operation than it could be. And on the framework side, it's pretty simple. It's a relative term, I guess. But you have your key generation, your cipher, and your master key store. It's 3 different Spring classes if you're a Java developer. And I mean, these all plug by default for JCE providers, which hardware encryption things have JCE providers. Most everything does. But if it doesn't, if you have an in-house crypto server, you can write your own one of these, one or all 3. Use it how you want. That framework is in place for that. So, it's an AMP. You install it, I think. I don't know if you want to correct me on that, but.
Well, yeah, 4.2 is AMP, and 5.0 is actually built into
Okay.
as a subsystem.
So it's built, yeah, it's built in, it's running as a subsystem. It uses Maven, as all of Alfresco is now on, and it needs to be enabled on all your clusters, otherwise they're not going to be able to read any of that data. So, and this is the last slide because I know I'm running out of time. The configuration, these are the properties. They might have slightly changed, but they'll be documented. But your general idea is you can specify a custom provider name for the JCE work. Where's your key store, if that's applicable, when you're using a file-based key store? What are your master key aliases that you want to use to encrypt the keys that encrypt the documents? What algorithm to encrypt the documents in? How strong? We default to 128 because Java does not have 256 unless you install the extra files. And then some just basic other parameters that you can use to try and optimize it with threading and batch sizes. And that's everything. Is there any? We're kind of out of time, but yeah.
You mentioned earlier that keys, you have setup keys and master keys. Is there a possibility that for whatever reason, if the keys are stored in a different system or a split key is used where half of the keys in the database, half of the keys in the lab, does Alfresco able to hold the keys from different places?
Not at this time, but you could, with the Spring classes there, you could probably implement your own that pulls it from two different locations, binds it together, and provides that capability. In that case, someone needs to know about the whole key if they're the one joining it, and that's kind of a concern as well.
So, the data at rest would be encrypted, nice.
Yeah.
How does this tie to search?
Right now, it's transparent on the content store, and so the search, whenever you're trying to index encrypted data, right now it's going to just index it because it's going to go through the repository to do that, so it'll decrypt it and index it. But with a lot of policies, you want to disable the indexing for things that are encrypted, and you'll just have to do that with the index control aspect at this time to prevent that indexing from happening, if that's the policy you're trying to get through.
Essentially, indexes will hold unencrypted data.
It will decrypt it to index it, so it will only hold the unencrypted data. You could encrypt the indexes as a whole by using a disk level, file system level encryption if you want, but sometimes that's not even good enough. Sometimes you have to turn off indexing for those types of documents by policy, by law, or whatever. Having fragments of documents somewhere else is a bad idea sometimes. Yep.
You said that you protect, you encrypt your content store, your indexes, and your database. It's basically that your data. But I think that, for example, places like the Alfresco Global, it could as well import that information like the database password,
Yeah.
the password or itself, the password itself that you showed. Is that something planned to implement
Yeah.
something that encrypts that?
I believe it's in 5.0. Yeah. To do Alfresco Global, there was a module I think Rich provided at some point, and it's been integrated into 5.0. Yeah, and you generate a key, you're able to put into another file an encrypted password, and then you have to secure that key somewhere else. But
Is it going to be included?
it's
That's in 5.0.
in 5.0. Yep.
What's
Yeah.
the performance
Oh.
overhead? What's the performance overhead? Have you done any?
Yeah, he might be a.
Well, yeah, we did some benchmarking and found out there was actually very low overhead to the encryption part rather than expected. I forget the exact number.
Well, it should depend on the developer, of course.
It does depend on the data size, and if you wanted to swap in your own cipher provider, if that got to be a problem, that would help a lot. Like Ryan mentioned, you might want to have hardware encryption to make that accelerate that a lot.
I know in the initial tests it was so low that it was just not significant at all.
But those like fairly small documents, you have those large documents.
Mm-hmm.
Yeah, with the hard bleed, vulnerabilities and kind of information leakage out of memory, has there been anything on protecting or clearing memory immediately after the use of these keys?
I did not with the initial implementation.
No,
Yeah.
no special, yeah.
Yeah, nothing special. I guess to avoid that, if you use the hardware, and it would never have that data. Although it's streaming unencrypted data into it, and where that gets stored could be a problem. But it never writes to the file system. It does it all in memory. So you would have to just be concerned about the memory part. Anything else? Okay, there's surveys on seats that I guess you're supposed to fill out, and there's a bowl in the back to put them in. So, thanks.